final talk in the session will be PanORAMA, Oblivious RAM with Logarithmic Overhead. This is a work by Savaro Patel, Giuseppe Passiano, Mariana Rekova, and Kevin Yao. And Kevin will give the talk.
All right, thanks for the introduction. So I'll just jump right in. So before we describe what an Oblivious RAM is, we should describe the scenario in which Oblivious RAM applies. So typically we consider Alice, or a client, that has a large document, a corpus document with a large amount of data that they want to store, but don't have the local memory to store it. So luckily we have another party called Bob, or the server, who is willing to store the data, or so Alice can outsource the storage to Bob. However, Alice wants to do this in a way that preserves the privacy of the data that's being stored. So the first idea that Alice could do is simply encrypt the documents. So using a client-side key, Alice encrypts all the documents before uploading to Bob. However, as Alice is retrieving and updating specific blocks of data, Bob will see the patterns of access to the encrypted data, essentially. So for example, Bob knows the most frequently used file, and it's been shown in practice that this can actually leak significant amounts of information about the data that's being stored itself. So one way to mitigate this risk, essentially, is to download the entire database. Of course, that's not really a feasible algorithm in the fact that bandwidth is expensive, and Alice doesn't even have the memory to store all of this locally. So this led to the construction of Oblivious RAMs by Goldreich and Ostrovsky in '96, and they essentially show that this can be achieved with only polylogarithmic overhead and bandwidth, and essentially hiding the patterns of access to the encrypted data. So this leads us to a very natural question. How efficient can ORAM constructions really be? So we'll talk about some lower bounds first before we get into our work. So in particular, in the seminal work by Goldreich and Ostrovsky in '96, they show this log n over log c lower bound for bandwidth of blocks, specifically for databases of n blocks and client memory of c blocks. However, it turns out these came out with some caveats, which are actually quite weird in a sense. The first is that the server can only move and retrieve blocks. Essentially, the server treats blocks as immutable balls, server locations as bins, and can move essentially balls within bins. Second, the construction only works for statistical adversaries in a sense, in that computational adversaries don't work, which is a little weird because a lot of ORAMs require encryption, which we don't really have statistical encryption. All right, so essentially Boyle and Naor a couple of years ago essentially formalized this balls and bins model and essentially showed all these caveats. And in particular, they showed something even stronger in the fact that they presented evidence that extending the lower bound for offline ORAM, so this weird ORAM where you get all the queries ahead of time, would essentially, any lower bound for an offline ORAM in general storage schemes beyond balls and bins would reduce to sorting circuits. So essentially, that's something that should be stayed away from because sorting circuits are very hard, or especially lower bounds. But this leaves credulence to the idea that an online ORAM lower bound might exist, and just this year, Larson and Nielsen showed that there exists a lower bound for computational ORAMs with logarithmic, an omega log n lower bound, and they removed all the caveats of Goldreich and Ostrovsky. In particular, they consider more than balls and bins, so in general, any type of storage encoding, and they consider computational adversaries. All right, so there's actually, in particular, there's really almost only two ways we know how to build ORAMs. The first on the left are called hierarchical ORAMs. Essentially, we'll get into this more later because that's actually our construction, so I'll be brief about it, but essentially, it has a bunch of exponentially increasing levels of sizes, and you have these deterministic shuffles, et cetera, and you do a query by adaptively going level by level from small levels to large levels. So this other paradigm called tree ORAMs actually only appeared very recently. And what they do essentially is they create a binary tree. And they assign each item or each block of the database to a random path in the tree. And then a query essentially will download the unique path from a root to a leaf of which a block is assigned to. But for some specific reasons, there actually happens to be something called a position map that's required. And then to do this, you recursively store it, et cetera, which also incurs some overhead. All right, so just a quick timeline and complexity of the work. So ORAM was, as I described, was actually started from the '80s by Goldreich with the square root ORAM. '96 was the first hierarchical ORAM, which got polylog and computation. And actually, there was like a die down. There wasn't much work on it until 2010 when Pincus and Riemann showed that cuckoo hashing could be applied to ORAMs. They had some slight small security issues, which were later fixed by Goodrich and Mitzenmacher. A couple of years later, the first tree ORAM appears. And essentially, path ORAM was the best construction at this point in time that was able to get order log n, or essentially achieve this lower bound that I've been describing, but it was only for omega log squared n blocks. And in particular, the best construction that we knew for ORAM for omega log n blocks happened to be this log squared n over log n by Kruslevich, Liu, and Ostrovsky. So as you can see, even though ORAM work only restarted in 2010, there's been a bunch of work. I've missed a lot of works, obviously, and there's been many paths, such as for MPC, FHE, practical, theoretical, etc. So it's been growing. All right, so now I'll discuss to you our work, PanORAMa. So in particular, we construct a new Oblivious RAM construction with essentially the best asymptotic communication complexity for omega log n block sizes. So this improves from the log squared over log len to just log n times log log n. We follow the hierarchical paradigm, so I'll describe that more in detail later. And interestingly enough, we can actually be instantiated in the balls and bins model where we only move blocks as immutable balls into server locations, which is sort of cool. So of independent interest, we have two new components that might be useful elsewhere. The first is what we call a multi-array shuffle algorithm. So from a high-level point of view, essentially what you get for this algorithm is you get a bunch of shuffled arrays, and you want that are all perfectly permuted, and you want to output just a single array that's perfectly permuted. So one way to do this is using an oblivious sort, but we show essentially by using the entropy of the input, you can achieve much better efficiency. The second is a new oblivious hash table construction, which actually has almost a similar problem in the fact that what we do is we assume that the input array is now perfectly randomly shuffled, and we show how to efficiently initialize an oblivious hash table in such a way that we can avoid oblivious sorts once again. All right, so these are the two components, and I'll go slowly, but first, I should describe to you what the hierarchical ORAM paradigm is, obviously. So essentially, like I described before, you have these levels that are exponentially increasing in size. So level I has essentially capacity of 2 to the I items. So when you do a search, you essentially adaptively search level by level from the smallest level to the largest level. So the smallest level is usually done by a linear scan. And what you do is for larger levels, you look up a searched item. I'll describe what lookup means later, but for now, essentially you look up until you find an item until you actually find the item. In which case, for all larger levels, you'll look up some random dummy item. And then at the end of the query, the item that's found is simply moved to the smallest level. So as I described before, levels have capacity to the I. So after 2 to the I queries, I can no longer query to it. So hierarchical ORAMs also have this second phase called the shuffle phase, which is essentially a deterministic schedule, deterministically scheduled shuffle. The idea essentially is at a certain point, since they're all 2 to the I size, they're all synchronized, when we have no more capacity to query for level I, what we're going to do is we're going to take all these levels that no longer have capacity, somehow shuffle them in a way that we can start looking up once again or querying once again. So how do we look up these search items on each level? Essentially, what we're going to use is an oblivious hash table. And essentially the main observation you use to achieve oblivious hash tables, because at first it seems like an oblivious hash table might just be an ORAM itself, is the fact that the access pattern we need to hide is only for non-repeating queries. So it's a very important thing that we'll use. We'll assume that because of the way the paradigm works, queries only come in non-repeating fashion. So for efficiency, there's actually essentially 2 things that we have to consider to make sure our ORAM is efficient. The first is the cost of the query itself, which is very important. But there's also this other cost, which is maybe sort of ignored, but it's this idea, how do we obliviously initialize these oblivious hash tables? How do we shuffle them together? And this actually happens to be the source of a lot of inefficiencies in previous work, and we show how to do this efficiently. All right, so the overview of our result essentially is just one line. We essentially leverage entropy and reuse it to shuffle more efficiently. So if I hope you guys get anything from this talk, essentially, is this idea of trying to maintain and reuse entropy in oblivious algorithm constructions. It's going to be very important. It allows you to do a lot more things a lot more efficiently than we couldn't do previously. So essentially, I'll show you that we actually use a slightly different paradigm for hierarchical ORAMs, which we believe is hopefully the right way to do it. But essentially, the idea is that let's look at these oblivious hash tables. What we're going to do during the shuffle phase essentially is take all these unqueried items and shuffle them together. But let's think about it from an overview for a second. We have an oblivious hash table, and we had constructed it in a way that we could have actually obliviously queried all these unqueried items, right? So the way they're actually currently, in however they're stored, should be in a way that's shuffled and hidden. And it should be, in some ways, easy to be able to extract these unqueried items in a way that's shuffled already, better than doing an oblivious sort where it's assumed that the adversary knows the location of every item. And that's what we'll show how to do later. So essentially, the first part of our oblivious hash table that we consider is these extract parts, where we take all unqueried items and shuffle them. The second is this multi-array shuffle. So what happens now is that the adversary sees these various arrays that are perfectly shuffled, essentially, let's assume. What you want to do now is somehow combine them in a way into one input array that's perfectly shuffled already. And finally, we can show that essentially, if you assume that you have this from the multi-array shuffle, we have to now be able somehow to build an oblivious hash table in an oblivious way from a permuted array. And it turns out we can actually do all three of these things without ever using an oblivious sort on a huge level. In essence, we avoid this extra log n factor that's inherent in all previous ORAMs. All right, so I'll start off by describing one of the components, which is the oblivious multi-array shuffle. In particular, what we do is we're going to be able to do a random shuffle in less than oblivious sorting time by leveraging the input entropy. In particular, we assume all these input arrays are perfectly sorted off the bat. And I'd like to note that this is inspired actually by some previous work with the cache shuffle that appeared in ICALC this year. All right, so yeah, that's that colored block that I'm going to discuss now. All right, so let's take a high-level point of view of this again. At the top, we have these L input arrays. We assume they're not too small, and we assume that they're perfectly shuffled. And now the goal essentially is to get this destination or output array at the bottom where everything is perfectly shuffled. So one way to obviously do this is to sample a random permutation and do an oblivious sort. However, it turns out if you were able to leverage this entropy from all these input arrays, you can actually do something a little weaker. And in fact, that's what we do. We show that it's sufficient to choose something like this assign function. This assign function essentially just describes, hey, for any specific entry in the output array, from which of these L arrays should I get that from? Should I get the input from? It doesn't matter from where, from which part of the array. We just need to specify the array it needs to come from. And in fact, this should be easier in some sense, and it is. Right? So we can avoid doing oblivious sorts. Okay, so the main observation used in constructing this oblivious multi-array shuffle is the fact that take any subarray of the output, and let's suppose, just for convenience, that the input arrays are geometrically decreasing in size or exponentially decreasing in size. In a sense, now we actually know an approximate proportion of the number of items that should be coming from this largest array, the second largest array, so on and so forth. So in particular here, if we take this, we look at this specific subarray D, we know that half the items should come from the largest array, a quarter of the items should come from the second largest array, so on and so forth. And this is something we'll use, since we assume that we do the assign functions chosen uniformly at random. All right, so the first step is to just sample this assign function. It turns out not to be too hard. I'll skip the details, but it's not quite difficult. But now, given this random assign function, what we do is, this is the idea that comes from the cache shuffle, is we take each block from all the input arrays and essentially pick one of these m prime input bins uniformly at random and place it into it. So this is done for all input arrays. So now what you can think of as each of the input bins is essentially a mixture of items from all the arrays in a correct proportion. And we also do this for the output bins. But the way we construct the number of input bins and the number of output bins is such that the input bins should be slightly larger than the output bins. So why is this important? Well, what we're going to do actually is we're going to pair up these input bins and output bins. And it turns out that these don't have to be too large. They can actually be polylogarithmic in size. So the reason why the input bins have to be larger than the output bins is that the property we want now is that whatever items are required from this specific output bin should be satisfied by the input bin. For example, if the output bin says there should be 5 elements from array L, then the input bin must satisfy this. And it turns out that if you pick the input bins just to be slightly larger by an epsilon fraction, this should always work for large enough arrays. And now, what I described before was that I like to avoid oblivious sorts on large arrays. But since these are polylogarithmic in size, we can just do oblivious sorts on them to be able to essentially place them correctly. However, of course, what I've described has a lot of leftover items. In fact, since the input bin has to be larger than the output bin, there obviously has to be more output bins, as well as since the input bins are larger, there'll be some leftovers. So essentially the idea is to take them, put them back into the pattern they were before, essentially. Since we assume that A1 was perfectly permuted, assuming we get back all of the items from leftover from the first block, and the leftovers should also be perfectly permuted, and so on and so forth for the rest of the arrays, and what you get now is you can recurse on this problem. All right, so that was one of our primitives. The other one that we do now is the oblivious hash table, which essentially the main thing that we focus on is the initialization phase, and doing this with less than oblivious sort efficiency. Oops. Yeah, that's these two parts. So we actually construct a new definition for oblivious hash tables, which has this extra properties that you build from a permuted input, and the extract, and you have to have this extract functionality, which is able to essentially extract an array of all the unqueried items in some random order. And for security, we want to have access hiding for non-repeating queries, like I described, and also we need that the extract the output of the extract is indistinguishable from a perfect random permutation. So it turns out that we're actually going to use something called oblivious bins, which are these mini oblivious hash tables, which are the inefficient ones that have been used previously, where we do oblivious sorts on inputs. But we're going to make sure it's okay in the fact that we only use oblivious bins on polylog n-sized items, polylog n-sized number of items. So essentially what we're going to use is pretty much the standard of what's been used previously in hierarchical ORAMs. Is something called this oblivious cuckoo bin, which is just an oblivious hash table. In particular, what you do is you somehow arrange the data into a cuckoo bin style where you have two tables. You query by picking one location from each table. And it's been shown previously by Gurvich and Mitsemacher way back that you can do this using an oblivious sort, essentially. All right, so I'll give you a very high-level view of what our oblivious hash table does. Essentially what we're doing is we're going to almost do something, I guess you can describe it almost as the opposite of what we're doing in the previous section, where previously we're kind of adding entropy, now we're just trying to remove it and structure it in a way that we can actually query easily. So the idea is we construct these bins, and we're going to start throwing items from this permuted array into these bins. Of course, we do this in a non-oblivious fashion, so the server sees how many items are going into each bin. If we try to build oblivious hash tables on each of these little bins right now, what happens is the server gets some density, gets some idea of what's happening with the density, and can figure out maybe information. You just can't get obliviousness essentially with this fact. So instead, what we do is the client will also privately sample another threshold, just slightly below this cutoff. And the idea essentially is that you can do this efficiently because you can actually simulate balls and bins distributions using binomials on the client. So what you're going to do now is we sample these little private thresholds, and these are the private thresholds from which we'll actually build our oblivious hash table over. So again, since the number of bins is n over polylog n number of bins, so each bin is expected polylog n size, we can actually use oblivious sorts on these little bins. So the idea essentially is we're going to do one oblivious sort where we remove all unused items that are above this private threshold but below this cutoff, just above, so that into an overflow buffer, which we'll deal with later. And then afterwards, what we do is essentially on these items that are remaining, you're going to build a cuckoo hash table, this oblivious bin, essentially using what's been the standard oblivious hash table. So once again, we have all of these leftover items. Naturally, we recurse. We do this again and again, and it turns out that we don't have to go too far. We only have to go log n levels because of once you get to the smallest level of n over log lambda or log n, in this case lambda is equal to poly n, what turns out is that you can just do an oblivious sort now in linear time. So what happens is we have these oblivious hash table that consists of log n levels, each with many bins, and each bin happens to be a small oblivious hash table. And we've avoided oblivious sorting on anything too large. So it turns out that querying actually looks very similar to hierarchical ORAM as I described before. What you do is for this really large bin at the bottom, you do a lookup query, and then you just move up. So essentially what you're going to do is for these levels with more than one bin, we had assigned these balls randomly previously using a PRF, and we do that once again to figure out which of the single oblivious bins to query. And once again, as soon as you find the item, you're going to start switching to a random query, and just like we had done with hierarchical ORAMs essentially. Okay, so recall that we also needed we need this extract essentially, right, which is somehow after we've done our queries and we decided we're going to reshuffle this into a larger level, we need to be able to extract all the unqueried items in a way that's perfectly randomly permuted. And it turns out that since we had distributed the balls initially in a random order, extracting is simply just taking each of these little bins, taking all the unqueried items, doing an oblivious sort, getting each of these little bins to be randomly permuted, and then concatenating the result, simply. And this can be shown to result in a perfectly random permutation. So once again, even for extract, as previous works would have done, they'd have to do an oblivious sort on all of these items. We just do oblivious sorts on little items to get this result back out. All right, so that's just a very high-level overview of our paper. There are a lot of details I've obviously skipped that you can look in the paper for, but our result again is that we get this log n times log n ORAM for block sizes of omega log n size. And of course, we have these two new efficient and independent building blocks, this oblivious multi-array shuffle and oblivious hash tables, which are essentially reusing entropy and being able to maintain them in a way that can be used later. And I think that might be a very cool thing that could be used for future Oblivious constructions. All right, so before I finish, some of you might be asking, where do we get the name from? This is the view from the PanORAMA Cafe, which we did a lot of our work. So, all right.
Questions for Kevin? I have a question. So you use a PRF, I guess, to determine the query positions. How hard do you think it would be to replace that with real randomness somehow?
For like statistical security, for
yes,
example.
Yes, for statistical security.
You can probably use, like, I think Agitai has a way of using a binary search tree to sort of replicate and store this real randomness on the server. You could do that, but that would incur a logarithmic overhead where you get back to the log squared.
Would you be able to somehow recurse your own construction? Would that work?
I would worry that if you recurse this construction again, you have to decrease by a significantly large amount to avoid the log logarithmic overhead.
I see.
Maybe it's possible. I don't see it right away.
Thanks. More questions? All right. To coffee.